Hello everyone, my name is Donald Tejan.
And I am Bruno Frischard. Today, we are pleased to present to you on behalf of our co-authors, Wielding Haptics, in situ prototyping of vibro-tactile feedback in virtual reality through vocalization.
Previous work has underlined the importance of haptic feedback for immersive virtual environments. Through different approaches, such as passive, active, or mixed haptic feedback, users are able to feel present in virtual worlds. State-of-the-art hardware supports haptic experiences through vibrotactile feedback, using either linear actuators or rumble motors. When designed correctly, vibrotactile feedback is able to generate very convincing experiences, such as haptic textures or haptic illusions. However, designing such convincing experiences still remains challenging. As underlined by related work, novice hapticians need more timely, hands-on interfaces leveraging direct manipulation to better grasp the experiences they want to design. Previous approaches for designing vibrotactile feedback focus on different aspects, such as vibration libraries or instrumental design. On the other hand, commercial approaches focus on manipulating low-level signal parameters through either graphical user interfaces or by converting audio into haptic signals. When considering these approaches in the context of virtual environments, there remains a very large disconnect between the design phase, which happens on the desktop computer, and the evaluation phase in virtual reality. This creates a very unintuitive and complex design cycle. To create convincing experiences, our approach, called Wielding Haptics, leverages the user's voice to design vibrotactile feedback while immersed in virtual reality. Our rapid prototyping cycle enables the designer to create the intended feedback while interacting with the object, after which they can immediately experience the result. In the following example, the user designs vibrotactile feedback for interacting with a virtual lightsaber. The designer activates the recording process and vocalizes the intended feedback during interaction. Our framework processes the user's vocalizations to generate the corresponding vibrations. An intuitive user interface allows the designer to adjust the mapping and parameters of the vocalization to vibration process.
Wielding Haptics builds on three core concepts to enable a rapid design cycle in the VR environment. To support in-situ design, designers directly interact with virtual objects while vocalizing. Based on a pilot study focused on vocalization strategies while manipulating physical objects, we infer four spatiotemporal mappings. A mapping is directly inferred and assigned to a vocalization based on the movements produced while recording. The vibrotactile feedback can be instantaneous, thus played only once, continuous and played repeatedly, adapt to the motion speeds, or associate vibration patterns to defined locations in space. As we do not assume designers have trained voices, this input mechanism is subject to inaccuracies. We compensate by leveraging fine-tuning modifiers also identified in the pilot study. They modify the vibrotactile feedback in real time and can contrast bursts in the vocalization, add randomness, or simply increase or decrease the overall amplitude and frequency. Designers have control over all these parameters through a vocalization layer inside the VR environment. They can switch mappings with remote pointing interactions and control sliders to manipulate the fine-tuning modifiers. Thunk, thunk, thunk. In this example, the designer wants to simulate a rock tumbling inside a box. Upon feeling the results, she is not convinced by the illusion and proceeds to fine-tune the signal. The expressiveness modifier helps contrasting the three bursts she previously designed and ultimately reach a better result. In this example, she would like to simulate different textures at specific locations of a slider. As manipulating this object implies moving on a linear axis, the positional mapping can be inferred. While recording, the vocalization will be associated to specific locations on the slider. The spatiotemporal mappings are not mutually exclusive. Designers can associate several of them to the same object by the means of multiple vocalization layers. In this example, that follows the one you previously saw, the designer records a second layer to produce the humming feeling of the lightsaber using a continuous mapping. To validate wording haptics, we conducted a user study involving novice hapticians. We presented them a set of 14 objects that induced various exploratory manipulations like shaking, sliding, stroking, or waving. They were free to interact with these objects the way they wanted and produce arbitrary vibrotactile feedback. Upon completing a design, we measured its quality through a Likert scale asking whether it matched the original intention. More details can be found in the paper. We conclude overall that wording haptics enable novice hapticians to design vibrotactile feedback in VR efficiently. We finally discussed design implications on the resolution of spatiotemporal mappings, the trade-offs in the fidelity of the fine-tuning modifiers, and how well can wording haptics generalize to other contexts like multiple objects manipulation.